Hello, welcome again. We are solving some questions of heat transfer. The topic is heat exchanger. Question number 25 to 20 common statement. The statement is a hot fluid at degree Celsius enters a heat exchanger at rate of 10 to the power 4 kilogram per hour. Specific heat is 200 joule per kilogram per degree Kelvin. It is to be cooled by another fluid entering at 20 with a mass flow rate 2500 kilogram per hour and specific heat 400 joule per kilogram per degree Kelvin. The overall heat transfer coefficient based on the outside area is 20 meters square. Is 250 watt per meter square per degree Kelvin. Assuming parallel flow. Question number 25. Effectiveness of 0.66 of option B 0.78, option C 0.62 and option D 0.69. Question number 26. The exit temperature of the hot fluid is option A 130.5, option B 142.25, option C 135.5, option D 160.1. Question number 27. The exit temperature of the cold fluid is option A 130.5, option 35.5 and option C 1.5 and option D 166.5. Heat transfer rate is option A 20.1 kilowatt, option B 19.8 kilowatt, option C 17.2 kilowatt and option D 32.03083 kilowatt. For hot fluid, the mass flow rate is given as 10 to the power 4 kilogram per hour, and second it is in kilogram per second it is 2.778 kilogram per second. Okay, and the specific heat of the hot fluid is given as 200 joule per kilogram per degree Kelvin. Inlet temperature is 200 degrees Celsius and MHCH, and this is your MH, and CH is this. So CH is your 555.55 watt per degree Kelvin. Okay. For cold fluid, MC is equal to mass flow rate, and that is given as mass flow rate of cold fluid is given as 25 kilogram per hour or 0.6944 kilogram per second. Specific heat is 400 joule per kilogram per degree Kelvin. Inlet temperature is 25 degrees Celsius and outlet temperature is unknown. So CC is your MCC CC, and it will be 277.76. So C is your C minimum by C max, and that is 1 by 2. Okay, so capacity ratio is 1 by 2, and as it is a parallel flow heat exchanger, so the formula for parallel flow effectiveness of parallel flow heat exchanger is 1 minus exponent minus NTU 1 plus C divided by 1 plus C. C is 1 by 2, NTU are number of transfer units, and it is equal to UA by C minimum. So U is overall heat transfer coefficient. U is given as 250 watt per meter square per degree Kelvin, and outside area is 20 meters square. And C minimum we have calculated 277 because out of these two CC and CH, the C minimum is 277.6, that is CC. So NTU here 250 into 20 divided by 277.76. Okay, so effectiveness is this. Putting in that formula, now we have all the values. We can find out effectiveness. Effectiveness is your 0.666. So answer to question number 25 is option A. Next question number 27, 26. So now effectiveness now we have effectiveness, that is 0.66, and in general the effectiveness is given by active heat transfer divided by maximum heat transfer, and active heat transfer can be taken either from the cold fluid or from the hot fluid. So from hot fluid, the heat transfer is MSCH bracket TH1 minus and C minimum divided by C minimum TH1 minus TC1. So MHCH is your 555.55 and C minimum is 277.76. TH1 is your 200 and TH2 is unknown, that is there, find out. So that is actual heat transfer, and that is the maximum possible heat transfer taking the highest temperature and lowest temperature in C minimum. and highest temperature is 200 and lowest temperature is the temperature of entering of cool enters temperature of cooling fluid enters, and this is the temperature of the hot fluid enters, and that is the maximum minimum temperature. Okay, so from this we can find out TH2. So TH2 is 142.25 degrees Celsius. So answer is B. Okay. Now question number 23 is TC2. So we have to find out TC2. So TC2 is again by the same method we can find out TC2. Now heat transfer is same. Whether this is a hot fluid or it is a cold fluid, and now we can take cold fluid. So cold fluid is MCCC TC2 minus TC1. You put the heat transfer from the cold fluid is this, and this is your C minimum TH1 minus TH1 TC1. So TC2 minus TC1 divided by TH1 minus TC1. So TC2 minus TC1 is equal to 0.66 into 200 minus 25. So TC2 comes out as 140.5. Okay, so from this we put TC1. We put TC1 is your 25 and solve it. Okay, then we can find out TC2. So TC2 here 140.5. So answer is 140.5, option C. So we can see that the TH2 and TC2 are very close to each other, and the flow is parallel flow. So it means this is because where the heat exchanger has very large area. That is 20 meter square is very large when we consider heat exchanger. So it means the hot fluid and cold fluid which is approximately at the same temperature when the heat exchanger is of large area. Okay. So now the heat transfer can be calculated by either of these, either MHCH TH1 minus TH2, or from MCCC TC2 TC1. So from this we can calculate heat transfer, that is 30.02 watt or 30.083 kilowatt. So answer is option B.